Hello students, in this lecture you will learn how to find potential and hence electric field of a conducting sphere when placed in external uniform electric field. To find potential and hence electric field, we use a spherical coordinate and using the zonal harmonics. That means at a given point, the potential and electric field will depend only on r and theta and not on phi. So here we have uniform electric field. It is uniform because the electric field lines are straight and they are equally spaced. Let us say that the field line is along the z axis. Next, take the conducting sphere. It is a neutral. Conducting sphere is a neutral. You keep it inside the external electric field. So now here what will happen is when you place inside the external electric field this sphere of radius a, then because of induction there is a separation of the charges. So one side will become negative charge. That means electrons will move in the direction opposite to the electric field and they will come here, and other side will become positive charge. And from the properties of the conductor which we have seen, inside the field will be 0, and these field lines will try to terminate perpendicular at a point on the negative charges, and it will try to originate perpendicular at a point from the positive charges, because of which the electric field outside the conducting sphere will get distorted, and close to the sphere it will not be uniform, but away from the sphere it will be uniform. Now as we have seen in the properties of the conductor that the surface of the conductor is the equipotential surface. So we will call this equipotential potential on the surface be phi naught. In the previous lecture, we had found the solution of the Laplace's equation in zonal harmonics, and the solution is expression for the potential, which is the function of r and theta. In zonal harmonic, it is a function of r and theta and not the phi. Then we had seen there are two solutions. One is r raised to n pn. This r belongs to zonal and this pn is a sinusoidal, it is harmonics. Now these are called as the Legendre's polynomial. Then other solution is r raised to minus n plus 1 and into pn. So now these are true for different values of n going from 0 up to infinity. So the general solution is a linear combination of those solutions. So we have written here summation of some constant r raised to n pn. Similarly, summation of some constant r raised to minus n plus 1 pn. So it is a linear combination of this solution. Now for n equal to 0, it is a0, r raised to 0, p0. For n equal to 1, a1, r raised to 1, p1. N equal to 2, it is a2, r raised to 2, p2. Then for this linear combination, that c's and a's are constant. The n equal to 0, so c0, n equal to 0 means r raised to minus 1, n equal to 0 is p0. Then n equal to 1, it is c1, n equal to n here is minus r raised to minus 2, and this is p1. Then n equal to 2, the cn is c2, 2 means 2 plus 3, that is r raised to minus 3, and n equal to 2, then it is p2. Then you can similarly write the higher order terms. So then we had seen that in the Legendre's polynomial, the p naught, value of the p naught is 1 and r raised to 0 is 1. So what remains is a naught. Then here a1, r raised to 1 is r, and value of p1 is cos theta. Then a2 r square, and value of P2 is 1 by 2 3 cos square theta minus 1 plus higher order terms plus now here again we substitute that C naught r raised to minus 1, P naught is 1, then C1 r raised to minus 2, P1 is cos theta, C2 r raised to minus 3, P2 is half 3 cos square theta minus 1 plus other terms. So let us call this solution of that Laplacian equation in the zonal harmonics as phi equal to this terms, and we will call it as equation 1. Now, as I mentioned in the beginning, that when the conducting sphere is kept in external electric field, nearby around it the electrostatic field get distorted, but far away then electric field is uniform. So at larger r electric field is nearly uniform, and hence the potential is due to this uniform electric field. So what we write here is electric field E when r tending to infinity. So uniform means it is like initial electric field, that is vector E naught, and also mentioned that electric field is directed along z axis. So that's why we write its magnitude E naught into k cap. Then here we know that E equal to minus d phi by dz. Z is the distance. So d phi equal to minus dz. When you integrate on both the side, integral of d phi is phi, and integral this minus e dz is the minus integral of e dz. Then here we write that the potential is minus integral of e dz. So it is written here. Then when you integrate, minus e naught comes out is a constant, integral of dz is z, and plus constant of integration. Then this from the spherical coordinate system, the z equal to r cos theta, we have not done it in our theory, but if you try to refer any book dealing with the spherical coordinate system, then z is equal to r cos theta. Like see, it is a conversion of the rectangular coordinate system into spherical coordinate system. So x has some expression, y has some expression, so z has expression r cos theta plus constant, that is equation 2. Then we started with the equation 1. So 1 and 2 should agree. This is the expression for the potential, this is the expression of potential at a particular point. So now here if you compare this, now a naught is a constant, so you can include it here. Now a1 r cos theta, see a1 r cos theta, if you compare it here with the equation 2, so a1 will be minus e naught. Then here this a2 r square, the theta here, other terms they are variable because r is variable, because that point P can be anywhere. So r is different, theta will be different. So these are variable. Since here what is there is a constant, so there cannot be variable terms there. So that means their coefficient a2, a3 and so on is equal to 0. So all a's from a2 onward must be set to 0. Then for this part of this phi, c naught r raised to minus 1. So c naught divided by r. So this is a potential which is inversely proportional to r. Now potential inversely proportional to the r is due to a point, a charge. Electric field is inversely proportional to r square. Potential is inversely proportional to r. It is because of a point charge. But in the conducting sphere, there are no point charges. So therefore, in this case, the C naught should be 0. Then C1 r raised to minus 2 cos theta can be there. But C2 r raised to minus 2 half 3 cos square theta minus 1 cannot be there, because this here the this part potential is inversely proportional to r cube, and that is true for the dipoles. Okay, so C2 is 0, similarly C3 is 0, and all C's higher than C2 should be 0. So therefore, this equation 1 can be written as phi of r theta. So A naught is there, then A1 is minus E naught, and what is there is r cos theta. Then other terms are 0 here. What is remaining here is C1 r raised to minus 2 cos theta. Now this phi r theta is for r greater or equal to A, that means outside the conducting sphere. In the previous slide, we had seen that outside the conducting sphere, we found this expression r greater or equal to A. Then on the surface, r equal to A is the radius of the conducting sphere. So when r equal to A, then this r equal to A, that means on the surface, and we have already mentioned that on the surface potential is phi naught. So now on this side, this phi naught, on the right hand side, we substitute here r equal to A and write this equation, which is A naught minus E naught r equal to A cos theta plus C1 A raised to minus 2 cos theta. Then if you compare this here, phi naught is constant, so A naught is constant. Whereas theta is a variable. So that means phi naught equal to A naught. That means, see, on the right hand side there is only constant, whereas here there is constant and variable, because theta is a variable. So constant we have equated phi naught equal to A naught. So that means this variable should be equal to 0, because it is the equality. So minus E naught A cos theta plus C1 A raised to minus 2 cos theta equal to 0. And when you simplify this, cos theta cancels, and what you will get is C1 A raised to minus 2 equal to minus E naught A, that is C1 equal to E naught. See here, cos theta cancels, C1 A raised to minus 2 equal to plus E naught A, and therefore C1 equal to E naught A raised to 3. Substitute this in the equation 3 which we have derived. We will substitute the A naught, value of A naught and the value of C1, and what you get here is phi of r theta equal to phi naught minus E naught r cos theta plus E naught A cube r raised to minus 2. So this is the cos of theta, and this is what we will get. So we have found in the previous slide the expression for the potential at the point P is equal to phi naught minus E naught r cos theta plus E naught A raised to cube r raised to minus 2 cos of theta. So here phi naught is the potential on the surface, r is the distance of that point P where we are finding potential from the center of the conducting sphere, and theta is angle made by that position vector from the origin to the point P with the z axis. Next, we have to find out the electric field from this potential. Now, in the zonal harmonic, in the spherical coordinate, that is in the zonal harmonic, where it depends upon r and theta, there are two components. Just like in rectangular coordinate in 2 dimensions, there are two components, x component and y component. In the spherical coordinate system, which depends upon r and theta, there are two components, er and e theta. And the theory of the spherical coordinate system, which we have not studied, says that r component is minus dou phi by dou r, and theta component is minus 1 by r dou phi by dou theta. Now here, let us consider er equal to minus dou phi by dou r. So minus sign is here. Then differentiate this with respect to r partially. So derivative of phi naught is 0. Minus E naught cos theta is constant because it is a partial derivative with respect to r. R is a variable, theta is constant. So minus E naught cos theta comes as a multiple. Derivative of r with respect to r is 1. Then here E naught a raised to cube cos theta comes as a constant multiplier. Derivative of r raised to minus 2 with respect to r is minus 2 comes as a multiple, and the power of r reduces by 1. So minus 2 minus 1, that is minus 3. Then in these two terms, this First of all, minus if we take it inside, minus minus plus. So all terms become plus. And E naught we take outside, cos theta we take outside, and what remains here, E naught cos theta is taken out, so is 1, and here plus, because minus minus plus, here also minus minus plus, E naught is taken outside, cos theta is taken outside, so what you get is 2a cube, and r raised to minus 3 become, goes in the denominator as r raised to 3. So this is the r component of the electric field. Similarly, theta component of the electric field is minus 1 by r dou phi by dou theta. So minus 1 by r, differentiate this phi with respect to theta partially. So phi naught is constant, derivative of constant is 0. Then since we are differentiating partially with theta, so that r is constant. So minus E naught r comes as a constant, and derivative of cos theta is minus sin theta. So minus minus becomes plus. Then E naught a cube r raised to minus 2 is a constant, comes as a constant multiple. Derivative of cos theta is minus sin theta. Then we take minus sign inside, r also inside. Then this becomes minus, this becomes plus. E naught we take outside, sin theta we take outside. So what remains there is here, this 1 r cancels. When you take 1 by r, 1 r cancel here, and this will become r raised to minus 3. So what remains inside is minus 1, and here a cube r raised to minus 3, which is a cube by r cube. So this is the theta component electric field, E naught into minus 1 plus a cube by r cube sine of theta. Next, we find the surface charge density of the conducting sphere when it is kept in the uniform electric field, that's sigma theta. And this for a conducting sphere, that electric field is sigma by epsilon 0. We have already proved it in the first chapter. Because of conducting sphere, the electric field is the sigma by epsilon 0, because for a conducting sphere in the external electric field, charges resides on the surface, and it has a surface charge density. So E equal to sigma by epsilon 0. So sigma equal to epsilon 0 E. Then on the surface, since the surface charge density on the surface, R equal to A. And this epsilon 0 is there, and ER, as we have found in the previous slide, is this quantity. And what we do here is, we put that the R equal to A we put here. So this is R equal to A, and when you put R equal to A, what you will get is A cube and A cube will get cancelled. So E naught 1 plus 2 cos of theta, that is epsilon 0 E naught 3 cos of theta. So this is the surface charge density of the conducting sphere kept in the external electric field. Then what is the total charge on the conducting sphere when it is kept inside the external electric field? Actually, since earlier the conducting sphere was neutral, then it is charged because of the induction, separation of the charges. But total charge is 0 because charge is conserved. So we should get the answer 0. And let us see how to get that equal to 0. So total charge Q is integral of, see now here integration is done in the spherical coordinate system with respect to theta. So this formula you should know. Again, we have not derived it. It is beyond the scope of your syllabus. Even in the textbook, you will not find the derivation for this. So integral of sigma 2 pi a square sin theta d theta. Then 2 pi a square is constant. We take it out. See, the integral is with respect to theta. So you cannot take this sigma and sin theta outside. Then here what we do is 2 pi a square is taken outside, and then we substitute for sigma from the previous formula. Sigma equal to 3 epsilon 0 E naught cos theta, 3 epsilon 0 E naught cos theta, and sin theta theta continued. Then what we do here is, we take this 2 inside and we take 3 outside. See, pi a square and 3 epsilon 0 E naught, it is a constant, is taken outside. We take the 2 inside. So inside 2 cos theta sin theta is nothing but sin 2 theta. So we have to integrate now from 0 to pi sin theta d theta. and integral of sine 2 theta d theta is cos of 2 theta divided by derivative of this angle with respect to theta. So derivative of this 2 theta is 2, and it is a minus sign. The integral of sine is minus cosine. Then when you substitute upper limit and the lower limit, what you will get is 0. This will become 0 because sine of 2 pi is 1 minus sine of 0 is also 1. So 1 minus 1 is 0. So the resulting quantity will become 0, and it is as expected. The total charge on the conducting sphere in the external uniform electric field should be 0.